Hi, I'm Alex Easterbrook. I'm a firmware engineer, and this is going to be the first video that I'm releasing on my YouTube channel, East Makes. I'm here to talk about Electromagnetic Field, which is a Glastonbury for nerds, is the tagline, or at least the unofficial tagline. You basically rock up to a field, you put a tent up, you get power and Ethernet to the tent, you go along to lectures. There are multiple stages, just like you'd find at Glastonbury, but instead of artists, you'll find interesting people from the hacking community or the making community giving talks about their specific fields of interest. And that's good fun. And when you sign up and you get your ticket, you also get given a conference badge. So these are the different conference badges across the years that that they've run the event. So the last year, so 2024, they made a badge called a Tildagon, and what this turned out to be was an ESP32 MicroPython badge. But one of the things that they did really well was, before the event, they made an interface spec open source for how to plug things into it, and this came out. Kai was probably the first person to have made one of these Hexpansions once it was made public. This was made public on the 18th of March. I had gone and made a little Hexpansion by 8:30 that evening and sent it out to fabrication with JLC. The people that knew how to make a Hexpansion instantly went out and made one. Since the event, I haven't been seeing a lot of people publicly hacking around with it yet. I want to make a video that goes through the process of me making a Hexpansion. It's probably also going to be the first PCB that I will be doing a solder paste reflow on. So it's a bit of learning for me, as well as documenting the process about how I get there. So I went on GitHub and I downloaded the source design files from KiCad, and I opened those up and I exported them to a step file. I imported the step file into Fusion, and I started designing how the keyboard would attach to the Tildagon. So that was basically giving the Tildagon a bit of a 3D printed chin. I actually went back through the design files for the earlier boards that EMF have done, and I'm using the same switches that they were on the 2016, 2018 sort of badges. I modelled the keyboard in this design after the BlackBerry keyboards that are floating around on AliExpress. So I had a screenshot of one open, and it's just your standard 3x10 rows with some shift and modifier keys at the bottom. One thing you can do is you can print this STL and fit it in and see how it feels. It felt really good. It felt like a return to T9 texting, and using the official EMF buttons, it was enjoyable. So jumping straight into the next problem is with the chin on the back of this, it's expecting to be mounted by going 90 degrees perpendicular to the Tildagon, but of course the SFP port isn't 90 degrees perpendicular. So I needed to then think about how I could design it so that the SFP port could go into the socket properly. So what I did is I put that rather long meander on the PCB so it would deflect a little bit. And that worked just fine for this application. So with the hardware and how it's going to be mechanically done, the next step is to start doing the schematic. So what I did was, first thing that I did was I went and looked at how other people were doing something like this. So I went and looked at how QMK type open source keyboards work, and they use a diode per switch, and they do this to try and reduce or eliminate ghosting. One of the things that you'll probably notice is that I'm not actually using a microcontroller with crystal with all of that on this. I've just gone and bolted a standard RP2040 little development module on the back, and I've gone and copied the reference SFP Hexpansion footprint. So this jump cut happens after about 2 to 3 hours of layout. So this is what the keyboard looks like with all of the traces laid out. It's got my little logo on the back. So at this point, it's ready to be sent to fabrication. Sent my Gerbers up to JLCPCB. The things to remember at this point is that yes, you have to be using a 1mm thick PCB for it to go into the SFP port. If you don't do this, you will have pain when your boards arrive and they're next to useless because you can't plug it in otherwise. The other thing is when you're saying that you'd like a stencil, don't get preoccupied by the dimensions tab. I did. I went for the smallest that they could do, which was still massive. If you go and say that you'd like a custom size, you can take the size of your board and add a margin and not pay over the odds in shipping like I did. It was the first time that I've done it, and it's definitely a lesson that I learned, so I would definitely do that going forward. So the really nice thing is when your boards get back from fab, you can replace the test 3D print that you've used with the real deal, and to see how they both compare against each other is really nice, especially when it's your first time. I've used stencils and I was blown away by how small some of these little cut throughs in the metal were and how well the stenciling process would work. Let's go and jump to how I got on with the stencils. Applying the paste was probably about 80% easier than I thought it was going to be. I am absolutely shocked by how little difficulty it was by using the paste and stencil method. It's something that I'm definitely going to be doing again. So this was me fitting the diodes. I was using the multimeter to tell which way the cathode and anode on the diode were, because they were so small and I didn't have a good enough magnifier to actually tell. Now the components are on, but they're not baked in place yet. So I had a nice little 1x1 inch reflow plate that I got from AliExpress. So I used that to reflow my board. Then I put some MicroPython on the RP2040 on the back of the keyboard and validated that everything worked. Now everything was soldered up with no problems first time. So that's a pretty good hit rate in my book. So after all of that process, this is what I am left with. You have a 3D printed back piece which bolts the keyboard PCB onto. You have the RP2040 there that is scanning for any key press. When it detects a key press, it's forwarding what key you have pushed up into the Tildagon over the serial port, which goes via the SFP. The default OS isn't aware of what to do with these messages, so what I've done is I've had to go and make a little app that will wait and read from that serial interface. But with that done, I'm able to type in hello world. And there we go. So that's, as far as I'm aware, the first full QWERTY keyboard that's been made for the Tildagon. Just before I close out this video, I wanted to mention just how much the documentation has improved on the EMF webpage for the Tildagon and for creation of Hexpansions. There's now comprehensive guides about how you can use a Hello World app, which is exactly what I did for making my example. And if there's anything that you can't find in the docs, there's always the IRC channel. There's a channel called EMF Badges. I went here in the process of making this video because there wasn't an example of how to use a UART on the docs. So by asking the question, I was able to find the information that I needed, and because I was able to get that working, I was then able to read input from my RP2040. So if you made it to the end of the video, thank you for watching. The process of doing this probably took me weekends and evenings in January to make this. I've learnt a fair amount of things, not just about the reflow process, but about cutting together and editing a video for YouTube. I've got a couple of projects that are on my to-do list that are about me learning 1 or 2 new bits of technology. So keep an eye out. If you hit the subscribe button, you'll be at least notified that when I release more content, you'll see it. So yeah, thank you for watching, and hope to be doing more interesting hacks to the channel pretty soon.